Now let's talk something about the von Neumann architecture, which is very relevant for our study. And surprisingly, this architecture has been uh, proposed like long back, 1945. A mathematician and physicist John von Neumann proposed a storage program model which follows till nowadays, right? So basically, he proposed there will be a memory, there will be a control unit with program counter, instruction register, and there will be an ALU, arithmetic logic unit, and there will be one register called accumulator, and your input mechanism can directly input some value into the accumulator or access the value directly from the accumulator on some output devices. That's his proposal. Now look at this system we just discussed. This has a surprisingly similarity of this model and this model, right? So his proposal is that your program and data are stored alike in the memory. As a device, memory does not distinguish whether some series of 10 bits is a data or is it a instruction. When it is accessed from the memory, it is the control unit who kind of decide and decipher if it is accessing a data or if it is accessing a piece of instruction from the memory. Okay, and it involves ALU for computation and so on and so forth. Programming model is a little bit different in that computational model where input directly goes to part of the ALU and results comes out of the ALU. It is more like you can say is a very complicated calculator model. It's really not a complex software programming model. But point is that it's very simplistic. But this has very similar thing as our control unit has instruction register, has program counter. It involves ALU. We don't have the accumulator though there, and we cannot access directly that accumulator register through our input device or through our output device. And it didn't have something like register file, so it is kind of an extra on top of the memory. But nonetheless, this is also a storage device, and this is memory. Of course, our program resides here, our data resides in this memory. Part of the memory will serve as the program area, part of the memory will be served as a data area, and we'll be accessing that. So the one issue with this von Neumann architecture is that it's a little bit slower in the sense, since we are using same device to store our data and the program, then what we won't be able to do that while we are accessing the memory, okay, while we are accessing the memory for the data access, at the same time we cannot do access for the program or instruction. Okay, so idea is this, like when we are writing back into the memory device or reading back from the memory device in the memory cycle or memory step, right? What we discussed, this 5-cycle step in the control system model. Since it is one single device, it is not possible to initiate an instruction fetch at the same time, right? So that problem was resolved by Harvard architecture, where it simply detached the instruction memory and data memory. So it says that its proposal is that we simply store instruction in a different memory module and data in a different memory module, so that control unit can simultaneously access, if needed, instruction and data, okay, together to speed up the process. Now, this advantage is also taken in the modern computing system. We call it a cache. So you probably heard that terminology: cache system, data cache, instruction cache, and so on and so forth. At that level, we basically use Harvard architecture, but overall computing system still follow the von Neumann architecture. So you can say in a nutshell that all modern computation system follows a mixture of von Neumann architecture and Harvard architecture. All right.